Ooh, all right. Now we got some different stuff going on here. Talked about determine power series converges. Let's look at another way to approximate Taylor series. What's an approximation? We already know. What's a remainder? Ooh, this is going to get spicy. So, I think we actually haven't really talked about an approximation that maybe we're supposed to know. That maybe in previous years I had talked about by now, but I don't think we've talked about it. So one way we know to approximate series is the alternating series. So we know, I maybe talked about it a tiny bit. I don't know. Yeah, I think we did talk about a tiny bit. So for an alternating series, if we add up the first whatever number of terms, we can get an answer. So the first, I don't know, the sum of the first 4 terms or something like that. The error is look at that 5th term, and the error has to be less than that. Error has to be less than that 5th term. So we're that close. And that's where we get this remainder idea. How close are we to what the answer is? Because I don't want to have to add up, obviously I can't add up an infinite number of terms. I don't even want to add up like 1,000 terms. If I can add up 4 terms and I'm within, 1/100th of the answer, maybe that's good enough. It just depends on the situation. In some situations when you're talking about super small things, that's not good enough. If you're talking about big things, you could be off by even more than that, and that would be okay. So the remainder is kind of the leftover bit that we're going to have, and it's the difference between the total sum of the series and the sum of the partial sum that we've built. So like this would be the 4th partial sum. So the sum of the first 4 terms. So the remainder is that leftover bit. Now this remainder is very similar in look to the alternating series remainder. I know it looks scary. So read those words. Here's what I'm going to tell you. This just means the n plus 1 derivative. So what that means is that's the derivative of the first neglected or ignored term. First term we ignore. I guess it's not really the derivative of that. That's the derivative involved in that first term. So I don't know if I want to say of. But if you think about, maybe this will be better. Here I am hemming and hawing, and I should just start writing stuff down. So if we think about what a Taylor series looks like, it was f of x naught, f prime of x naught, x minus x naught, f double prime of x naught, x minus x naught over 2 factorial. And then the general term was the nth derivative of x naught, x minus x naught, and then the n factorial down here, so the n up here. So that's kind of the general term. Notice that this just looks like the term right after that, the n plus 1 term. So that's what I'm talking about. It's that next term. So it's just like the alternating series remainder in that it's the next term that we pay attention to. The difference is, you see how there's a c there and not an x naught? That's where things get different. And so basically what that c is it's some number between x and x naught where the derivative is bigger, like the biggest value. So for example, if I have like a sine function, the biggest the sine can be is 1, so the biggest that derivative could be, if sine is the derivative, the biggest it can be is 1. So it doesn't matter if at x naught the derivative is 1, this is the derivative's the maximum derivative's value is basically what we're looking at here. Another book I had talked about how it's the max derivative. That green part is the max value of the derivative in the interval. Let's look at some specific examples and see if that makes a little bit of sense in your brains. Now we're going to look at a specific example here and see if we can figure some stuff out. So our job here is to give LaGrange's form for the remainder, R4 of x, for the square root of x centered at 1. So I went ahead and built what that series might look like. And so the P4 would be the 4th degree polynomial. It's actually everything before that green bar. This piece is going to deal with the remainder, but let's take a look at what's going on. We have x to the 1/2. Derivative of that is 1/2 x to the negative 1/2. That's the first derivative. Second derivative, negative 3/2. Third derivative. Fourth derivative. And then fifth derivative. So that's going to be 7 times 15, which is 70, and 35, 105, over 32. So at that part's going to be useful for us. That's going to be what the fifth derivative looks like. That 7 over 256 is going to be related to that. Because if you take 105 over 32, sorry, I'm processing, over 5 factorial, that's where that 7 over 256 idea comes from. But anywho, so for the Lagrange's form of the remainder, we want to know the maximum value, or the value, C value. So let's just plug in C for that. So we're going to have 105 over 32. I'm going to write that as C to the 9/2 down here. Of course, I wrote down X, not C, silly goose. I don't know what C is, so it's some number in the interval. Don't know what that interval is. Don't know what that number is. And then X minus 1 to the 5th. And that's for some C between, so C is between 1 and whatever X value we choose. So if we choose an X value of like 1.2, maybe that would be helpful. I don't know. I feel like I'm jibber-jabbering here and I don't know how helpful I'm being. But okay. Suppose I choose an X value, like I want to approximate this for when X is 1.2. So I want to approximate the square root of X for when X is 1.2. If I add up the first 4 terms of my polynomial, which are right here, I will be within 1.2 minus 1 to the 5th. So, okay, if I'm picking between 1 and 1.2, and I'm taking the 9/2, it's not going to make that big a difference, but I would put 1.2 in here to the 9/2, because that's going to be, no, that'll be bigger. So actually, I would pick 1, because it's a fraction. So it's going to be 1 to the 9/2. That would be the number I would pick. And I would be within this of the answer. So if you do that calculation, you'll be within that of the answer. And I just put some buttons, so that's 0.00105. So if I add up the first 4 terms, I'm that close to what the true answer is. I'm off by like 1,000th. So you could calculate what 1.2, that might be a good exercise for you to try right now. Plug in 1.2 for X right there, right there, right there, and right there, and add up those first 4 terms, and then do the square root of 1.2 on your calculator and see that the difference is not bigger than that. All right, so let's try again. Use appropriate Maclaurin series to express the quantities in series form. Use Lagrange's form for the remainder to bound the error, and using a 5th degree Maclaurin polynomial to approximate the given quantity. Find the smallest value of n so the nth degree Maclaurin polynomial approximation is to the given quantity is guaranteed to be within 10 to the negative 6. Okay. So the Maclaurin series for e to the x, 1 plus x squared over 2 factorial plus x cubed over 3 factorial, etc. And so, if I were to add up to the 5th degree. So maybe I should just write that down. So x to the 4th over 4 factorial, x to the 5th over 5 factorial, and so on. So the first thing I don't pay attention to is that x to the 6th over 5 factorial term. And by x to the 6th over 5, I mean x to the 6th over 6 factorial. What am I talking about? All right. So that's what the form's going to kind of look like. Now, all the derivatives of e to the x, well, I guess, okay, so e to the 0.9. Maybe I should do that approximation. So plus 0.9 plus 0.9 squared plus 0.9 cubed plus 0.9 to the 4th, and then plus 0.9 to the 5th. That's next, 0.9 to the 5th over 5 factorial. So actually I should use an approximation here, because this is an approximation. That's the series, and that's the approximation of e to the 0.9. To figure out the LaGrange's form for the remainder, I have to think about what the derivative looks like. So what the 6th derivative looks like, it looks like e to the x. So the 6th derivative looks like e to the x. And then I've got to do x minus the center, but that's just x. And then over 6 factorial. And I regret putting this here. I should do e to the c, because I don't know what c value I'm going to pick. I'm going to pick a kind of maximum value for that. And then x to the 6th, so that x is actually going to be, in this specific case, that x is going to be your 0.9. So it's going to look a little bit like that. All right, let's take a look where we're headed, or what kind of the answers are here, because I think that might help. Okay, so we've got, that's the general series for e to the x. This is the general series if I plug in 0.9. I only wanted to add up the first 5, so I wrote down what that looked like. Your general form of the Lagrange is that next term, the next derivative, the n plus 1 factorial x to the n plus 1. Because x naught is 0 here, we can get more specific. So in this case, we added up the first 5, like I wrote on the previous page. So we're looking at the 6th derivative there. We're looking at 6 factorial and 0.9 to the 6th. Now, I have an e to the c right here, and I wrote a note. We use 2.7 as an approximation for e. We can't use e to the 0.9 as we don't know that. Because we're trying to approximate e to the 0.9, I can't then use e to the 0.9 here. So you sometimes have to choose values or be given values of what to put in this spot here. So sometimes that one that I'm guessing that's the part that you guys find most confusing. I know it's the part I find most confusing. Sometimes they have to give us that value. So as I said, in this one, we're going with the 2.7. The 0.9 to the 6th over 6 factorial, that's the piece from that next term, so I don't think that's the scary part. The derivative value is the scariest part. All right. Now, if we think of this in general, so what we're going to put for that e to the c value, no matter what c, because this is the e function, and then we're going to have the 0.9 is the thing we're plugging in, and we want to look at some random term, so the n plus 1 term, because this is the last part of that question, which was finding an error that's less than 10 to the negative 6, because sometimes you want to get things as close as some number. In this case, we picked 10 to the negative 6. So if you look at this equation, again, this is that 0.9 to the n plus 1 factorial, so that comes from that next term. This is the approximation for the derivative, the max approximation for the derivative, the value of the derivative somewhere in that interval. And then we solve this equation. If you plug in n values, you can figure out that once you get to 9, that will be, you'll have less than 10 to the negative 6th. All right, now, obviously the numbers on that are a little wonky. Generally speaking, when we're asked for that, the numbers will